let's talk about acids and bases. Acids, when you think about acids, you might be thinking of your stomach acid, HCl. You might be thinking of a lemon. And for bases, you might be thinking about baking soda. It's a baking soda. You might be thinking about sodium hydroxide. Okay. Acids are usually pretty sour. Okay. And bases, they're pretty bitter. Now, this ain't really a good definition for acids and bases. Like, acids are sour, bases are bitter. Like, things that aren't bases can still be bitter. So this is why there are actually several definitions for an acid and base, but let's talk about the first one, and this is called an Arrhenius acid. Alright. An Arrhenius acid is a substance that has H in its formula. So, a substance that has H in its formula, and when dissolved in water, it produces hydronium ions or H plus ions. So Arrhenius acids, they're just a substance that has H in its formula, and this produces H3O or H plus ions when dissolved in water. Now think about it. Okay, so let's say if we have an acid. So one example of acid, this is called sulfuric acid, H2SO4. In sulfuric acid, we know that this is an ionic compound, right? SO4 has a 2- charge, and H, it has a +1 charge. Okay, so this is an ionic compound. When you dissolve this in water, we know that this breaks up into H plus ions and SO4 2- ions. So it's actually 2H plus ions and an SO4 2- ion. Okay, so obviously you can see from this equation that this is an acid because it releases H plus ions. And you might be confused. What do you mean when it produces hydronium ions? Well, think about water, okay? Think about H2O. What happens is this H plus ion can get attached, you can think about it, to the H2O molecule. So imagine if, so you have H2O, right? And what happens is you got a hydrogen ion that's kind of being attached to this H2O molecule. So you're adding a hydrogen, so it's H3O, and the hydrogen has a plus charge, which is why you have H3O plus in its formula. So you have an addition of hydrogen, and you have an addition of a charge. An Arrhenius base is a substance that produces OH- ions when dissolved in water, and it has to have OH in its formula. So NaOH would be an example of a base. It has Na plus ion and OH- ion. It has OH in its formula, okay? So this is an ionic compound, so when it dissolves in water, it dissociates into its individual ions, Na plus and OH-, which is what is required for a base. Now the problem is, you have substances like ammonia, right? This is actually a base, but the problem is it doesn't have OH in its formula. So this definition is kind of outdated, and there's actually another definition for acid and base. So let's look at it. So the Brondstead-Lowry definition of an acid is H plus or proton donator, and Brondstead-Lowry base is H plus or proton acceptor. Now when I'm talking about H plus and protons, they're the same thing, okay? H plus ions and a proton, they're the same thing. Because a neutral hydrogen atom has one proton and one electron. Now what happens when this one electron gets stripped away of this hydrogen? So you're taking away an electron from a hydrogen. Well, if you take away a minus charge, you're just going to be left with a plus charge. And you only have one proton left because it's hydrogen. So that's why H plus ions and protons are the same thing. Okay, now I've drawn a reaction and I've drawn a diagram of the reactants. So what do you mean? What do I mean by proton donator? What do I mean by proton acceptor? What's happening in this reaction? Well, what happens in this reaction is you can look at one of the hydrogens here. Let's look at the hydrogen here. All right. So we know that this hydrogen is sharing an electron with oxygen. But what this hydrogen is going to do, it's going to dip, all right? It's going to go to the nitrogen, but it leaves its one electron behind, okay? So it's going to dip, and you can think, so you have nitrogen, and now you have 4 hydrogens and a plus charge. All right, so now ammonium, right? NH4 plus. This is going to look something like this. So you have 4 hydrogens. And this is going to have a plus charge. Right? The hydrogen left its electron behind, meaning that it's an H plus ion. And because it left its one electron behind, this means that this part of the molecule, this is going to have a minus charge, aka the OH ion. You see? So this one hydrogen, it just dipped. It left the electrons behind, which means this part of the molecule is negatively charged. And because the hydrogen left its electron behind, the hydrogen itself is of H plus ion because it doesn't have that electron left. Now, you can see from this reaction, this looks all confusing and stuff. I want you to identify which one's the acid and which one's the base, or in the reactants. Well, you can see that H2S is actually giving NH3 an H plus ion, so that it forms NH4 plus, which is why this thing that donated the proton, this is actually your acid, and NH3, this is your base. Now, the thing that got donated the proton, the NH3, it becomes NH4 plus, and this thing is called the conjugate acid. And what this means is that this NH4 plus can actually spit out this H plus ion. So it can technically act as an acid, right? It can release this H plus ion that it just gained. And the thing that lost the H plus ion, so the thing that was originally an acid and became a negatively charged compound, this thing is called your conjugate base. And in the conjugate base, your negatively charged compound can react with a positively charged hydrogen ion to form back to your original product. So you can see that acids and bases, they differ from a difference of 1 proton. Try to identify which one's the acid, which one's the base, which one's the conjugate acid, and which one is the conjugate base. Okay, the thing that donated a proton, we can see that HF became F minus, which means HF donated a proton to H2O, right? The proton left the fluorine atom and it turned into a fluoride atom. It lost that hydrogen, right? So this would actually be your acid and the water would be your base. Now, the thing that H2O became, the thing that the base had become, is H3O plus. And that's going to be your conjugate acid, okay? So I'm just gonna say this here. The thing that the base became is the conjugate acid. The thing that the acid became is the conjugate base. So they're kind of like opposites of each other, okay? Base becomes conjugate acid because it can spit out the proton that it gained, right? It can spit out this proton that it gained, and right? And the fluorine atom, it can accept a proton, which is why this is the conjugate base, all right? Now let's talk about pH. All right, so you might have heard of the pH scale. All right, so right here is the pH scale. 7 is neutral. 7 is neutral. This is 0. This is acidic. And this part is 14. And this is basic. So things that are above a pH of 7 and neutral stuff like water. Alright, water is a neutral compound. Things that are more alkaline or more basic than water, you would call it, have a pH higher than 7. While things that are acidic, like your stomach acid, they have a pH lower than 7. Alright, now, the pH scale, this is a logarithmic scale. What do I mean by that? Alright, so let me just draw out all the... So let's say we're comparing something that has a pH of 6. Let's say we call this X. And let's say we have something that's 7. Let's call this Y. You wouldn't say that. What would you say about X and Y? You would actually say that X is 10 times more acidic than Y. Right? So you would actually say that the thing with the pH of 6 is 10 times more acidic than the thing with the pH of 7. Or you can say that the thing with the pH of 7 is 10 times more basic than the thing with the pH of 6. Alright? So a jump from 6 to 5, once again, 10 times increase. A jump from 6 to 5, well, 10 times 10, that would be 100 times increase in acidity. How do you actually calculate the pH though? You gotta use this formula. Negative log of the concentration of H plus ion, or negative log of the concentration of H3O plus ion. Alright, so for example, if I said the H plus ion concentration is, let's say, 1.0 times 10 to the negative 4 molar, you would just put negative log of 1.0 times 10 to the negative 4, and your calculator would spit out 4. So something with a concentration of 1.0 times 10 to the negative 4 has a pH of 4 for the hydrogen ion. Let's say the hydrogen ion concentration was 1.0 times 10 to the negative 3. Negative log of 1.0 times 10 to the negative 3, and you're going to get 3. So you can see, as the concentration of hydrogen ion increases, your pH decreases, okay? So as concentration of H plus ion increases, your pH is going to decrease, alright? H plus ions in your solution equals more acidic. However, remember when we said that OH minus ions, things that release OH minus ions, are basic? Well, just like how you can use the concentration of H plus ions to calculate the pH, you can calculate the pOH, which is just a constant negative log of the concentration of OH minus ions. So let's say your concentration of OH minus is, let's say, 1.0 times 10 to the negative 8. And when you put this into your calculator, you're going to get that this is going to be negative log of 1.0 times 10 to the negative 8. And this is going to spit out 8. So something with a concentration for OH, the OH minus ion of 1.0 times 10 to the negative 8, will give you a pOH of 8. Now, let's do some pH calculations. Let's say if the concentration of hydronium ion, let's say it's equal to 1.8 times 10 to the negative 4 molar. Alright. Calculate the pH. So the pH is actually going to be, so negative log of 1.8 times 10 to the negative 4. Alright. And your calculator is going to give you like 3.74 and then blah 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 blah. Alright. And your answer, well, SIGDIGs for pH is actually pretty weird. So you see how our initial concentration is 1.8, right? It has 2 SIGDIGs. We're going to round 2 SIGDIGs after the decimal, right? So this thing in front of the decimal, the stuff in front of the decimal, they don't really count as SIGDIGs for pH. Only the things behind the decimal, they count as actual SIGDIGs for pH. So you would actually round 2 units after the decimal, aka the reason why your answer would be 3.74 as your pH. And this would be acidic, right? Because your pH is under 7. Next, let's say the concentration of hydroxide. Let's say this is 7.2 times 10 to the negative 3 molar. So when you put this into your calculator, you're going to get negative log 7.2 times 10 to the negative 3rd power. And it should spit back 2.1426 blah blah blah, right? And remember, we started out with 2 SIGDIGs, and we got to go 2 SIGDIGs after the decimal. So your answer would be 2.14. Another formula you got to memorize: pH plus your power of hydroxide equals 14. All right. So this is kind of why the pH scale is 14. All right. Let's say if your pH is 7. All right. That means your pOH is also 7. And this adds up to be 14, right? In something that has a pH of 7, it's neutral, meaning the concentration of your hydronium ion equals to the concentration of your hydroxide ions. So you got the same amount of stuff, which is why the pH is 7. So let's say if our hydroxide ion concentration, let's say this is 1.2 times 10 to the negative 9. Negative log, right? We're trying to find the pOH, right? pOH equals to the negative log of 1.2, alright, just molar, alright. So 1.2 times 10 to the negative 9 molar. So we're just going to put 1.2 times 10 to the negative 9. And we're going to get 8.92 as your pOH. If your pOH is 8.92, from this formula, you can just sub this in, right? So pH plus pOH, in this case we know that's 8.92, equals to 14. And doing some basic algebra, we get that the power of hydronium is going to equal to 5.08. And that's going to be your answer. So this is a titration. So we're going to be talking about titrations now. A titration is when you're using, let's say, you have acid, right? You have 50 milliliters of acid, but you want to find out the concentration of acid in the solution. So you would set up a titration. So in the Erlenmeyer flask, so in this flask thingy, you're going to add, you obviously have your acid, and you have an indicator. Now the indicator, if you look at table M, it tells you all the acid-base indicators. And indicators under a certain pH range change color. For example, let's look at bromithimal blue. Alright, so this thing changes color under a range of 6.0 to 7.6. And this changes from yellow to blue. Alright, so anything below 6.0, it's going to stay yellow. And anything above 7.6, it's going to stay blue. The only difference is that if, let's say, you have something with pH of 9 and you use bromithyl blue as an indicator, it's going to be a really dark blue, right? Because this is way above its color changing range. And same thing for the yellow. If you have something below the pH range for your indicator, that thing is going to be a really dark, in this case, yellow. All right. So you would put an indicator inside of the flask, and you would neutralize the acid with some base, right? Because you know acids and bases, they neutralize each other. So we put a certain amount of base into this solution until just enough acid has been neutralized by the base that, like, the indicator starts changing color. And when the indicator fully has changed color, that's when you know your titration is over. Okay, so the point where the moles of base added, so you know the amount of NaOH you added, has neutralized the HCl, aka the acid. So when the base neutralizes, has completely neutralizes the acid, this is going to be called your equivalence point, alright? Equivalence point. Alright, so just this is like the perfect amount of base that neutralizes the acid. And the end point of your titration, so this is when you should stop your titration, indicator changes color permanently. That's when you know that you have reached the end point of your titration, right? So at your end point of the titration, it's like 100% guaranteed that you have neutralized your solution. Let's look about titration curves. So remember I was talking about the equivalence point? Well, this graph shows the relationship between the amount of base added and the pH, its effect on the pH. And obviously, if we add more base, the pH is going to increase, right? pH is going to increase, which explains this trend, this increased trend. Now, this X right here I marked is the equivalence point, and this is when the pH is 7. All right, this is the point, I'm just going to repeat it again, when you have found the exact amount of base, in this case, that neutralized the acid. All right, and because strong acids, they neutralize strong bases, strong acids neutralize strong bases, and vice versa, their pH is going to be exactly 7, right? Because acids, they have a pH below 7. Bases, they have a pH above 7. So it makes sense that, you know, when they're neutralized each other, their pH is exactly 7. Alright, so let's write out our reaction for our titration. So HCl reacts with NaOH to yield H2O, and our salt is NaCl. At the beginning of our titration, right, so in this, all these points are marked, right? All these points are marked. I'm going to be talking about what's happening on a molecular level. While in this case, we have HCl in our solution. So at the beginning of our titration, when we haven't added any base yet to our Erlenmeyer flask, there's only going to be HCl in our solution. And HCl is a strong acid. meaning that it's going to release H plus ions and Cl minus ions. So strong acids, right? Strong acids, they have a really low pH. And the reason why, well, one of the reasons why is because they release a lot of H plus ions when you put them in water. And remember, H plus ions makes solutions acidic. Then, as you add some base, some of the base is going to react with some of the acid to yield NaCl. So you're going to have Na plus ions and Cl minus ions. But you haven't completely neutralized the acid. So there's going to be excess amounts of acid left, right? You added some base, but you're still not at the equivalence point, right? So you still haven't neutralized the acid yet. You added some base, but all of the base is just going to get overpowered by the acid, right? There's too much acid. You haven't added enough base yet. So all the base is just going to react. There's still going to be acid left. And because you added some base, it's going to react and form some NaCl, right? As you can see in the equation. And because NaCl is in water, well, it's going to dissociate into its ions, which is the Na plus ion and the Cl minus ion. At your equivalence point, you found the perfect amount of acid to neutralize your base, which means that there's going to be no acid left and no base left, right? They completely neutralized each other, and you're just going to have your salt. Then, if you keep adding more, well, you're adding base, right? You're adding more base, but you already completely neutralized all the acid. All the acid has reacted, so you're just adding base for nothing. And then you're just adding Na plus ions and OH minus ions at that point. So this is just finding out which ions are present at which moment during the titration, all right? So at beginning of a reaction, you only have your acid. A little bit further from the beginning point, you're going to have some of the salt, you're going to see some product, and you're going to still see your acid. Equivalence point, you're only going to see your product. And after the equivalence point, you're going to obviously still have your salt, right? Your salt ain't going nowhere. And you're going to have excess base, all right? So at this point, excess acid. And then at the end, you have an excess amount of base. This is how to actually solve for, the molarity of your acid based on titration data. So let's say we have a 0.15 molar NaOH, and we have 15 milliliters of this. And this is what's going to be used to titrate to find the concentration of HCl, all right? And the thing we're trying to find the concentration of, this thing is going to be called a titrant, all right? So our titrant is going to be our acid, which is 0.15 milliliters, but we're trying to find out the concentration. What we do is we first write out our reaction for the titration. In the reaction, we can see that the mole ratio of acid to base is 1:1, right? 1 mole of acid equals 1 mole of base. For every 1 mole of acid, we have 1 mole of base. And if this thing applies to our reaction, we can use this formula, MAVA equals MVBV, where MA, that's molarity of acid, times volume of acid, equals the molarity of base times volume of base. And this equation only works if the mole ratio of your acid and base reaction is 1:1. That's the only time it works. So our molarity of our acid, we don't know that. We don't know the concentration of acid. Call that X. We know the volume of our acid, 0.15 milliliters, but we want this in liters, so we divide this by 1,000. We have our concentration of base. That's right there, and we have our volume of base. That's 15 over 1,000 liters. So solving for X, if you put this into your calculator, I'm just going to do this real quick. So plug this into your calculator, and then you should get 15 NaOH. All right. So X equals NaOH. No. Plugging this into your calculator, you should get X, which is your molarity of the acid, equals to 15 molar HCl. And let's say we do another titration. Let's say we have 0.623 molar of HCl. Let's say we have 42 milliliters of that. And let's say that we have 35 milliliters of NaOH. That's our titrin. But we don't know the concentration of NaOH. So that's going to be... we don't know this. So from the reaction before, this is the same reaction. We know that the mole ratio is 1:1. So for every 1 mole of acid, there's 1 mole of base. Which is why we're going to use MAVA, MV, MBVB. So we don't know the molarity. I mean, in this case, we know the molarity of our acid. That's going to be 623, my bad. 623 molar. And we know that the volume, that's going to be 42 over 1,000 liters, right? And this is going to equal to our concentration of base, or molarity of the base. We're trying to solve for that. Let's call that X. And we know the volume of the base. That's 35 over 1,000 liters. So then, the rest is just calculator work. So 42 over 1,000. And then you just have to divide this by 35 over 1,000. And you should get X equals to 0.7476, and rounding to the correct number of sigdigs. In this case, we're rounding to 2 sigdigs. So we should get 0.75 molar of the concentration of our base, because that's what we're trying to solve for. So that's going to be molar NaOH. Now, burettes are a strange thing. So the regents are probably going to ask you this. They're going to give you initial burette reading. So the burette is the thing that's you're using to titrate, right? So, remember you have your Erlenmeyer flask, right? And then this would be your burette. This is your burette, the thing that you're slowly adding to your solution. The burette is a strange thing because if you zoom in, right? If you zoom in, the values are backwards, right? Normally, in a container, you would have, this is 0 milliliters, 10, 20, 30, 40. But this, in a burette, this is backwards. This is like this, backwards. So, let's say, I don't know, you start off with, in this case, let's say you start off with, okay. Let's say you start off with 10 milliliters. All right, so you start off with 10 milliliters of, let's say, base. And you're going to use the base for the titration. And once you use the base, you found out that your final burette value, that's going to reach 20. It reaches 20. All right. So it reaches 20. Final value, 20 milliliters. To find the change, well, you just have to subtract the final value by what you had initially. So to find this change right here, so to change in your, in this case, burette, or change in this case, the change in base, so the change in the amount of base that's inside this burette, you would subtract your final value by your initial value. So in this problem right here, to find the amount of base we used, you would subtract your final value by your initial value. and obviously set the units to milliliters, and you're going to get 1.9. This is pretty easy as well. Alright, now remember how I said MAVA, MVVB only works if the mole ratios, so mole ratio of acid to base is 1:1. If the mole ratio isn't 1:1, you just gotta use stoichiometry. So what I mean by that is, let's say that we have HCl. Alright, so we have some acid we're trying to titrate. So let's say we have 10.2 milliliters of acid. And in our titration, we're going to use CaOH2, so calcium hydroxide. And we're going to use a 0.54 molar solution of this and 53 milliliters of this. In a titration, you should always write out your reaction first, because you want to find out if your mole ratio of acid to base is 1:1. So let's write out the reaction. So milliliters of acid, HCl, so HCl, CaOH2, and this is going to yield H2O and CaCl2. Now we got to balance this equation. We have 2 chlorides on this side, so we got to put a 2 here. And in addition, you can also see that we have 2 hydrogens, 2 extra hydrogens, and 2 extra oxygens. So in this case, we got to put a 2 here. 2 times in this invisible 1 is 2. 2 times this invisible 1 is 2. So we have 4 hydrogens. Now we have 4 hydrogens on this side as well. We have 2 oxygens on this side, 2 oxygens on the other side. The rest looks clean. We balance the equation. Now we can get titrating, you feel what I'm saying? Alright, now we can finish this titration. So we have molarity. First of all, we have milliliters. Remember, if you have milliliters, convert this to liters. So 1, 2, 3. So it's going to be 0.053 liters of our base. And what we're going to do is we're going to convert to moles. So in this case, we have molarity. That's 0.154 moles for every liter. So if you put this into your calculator, you're going to get 0.008162. I'll round at the end. So you have this many moles of base. Alright. Now in the reaction below, there's 2 times as much acid as base. Meaning that if we have this much base, we must have 2 times this amount of acid. So we have to multiply this quantity by 2 to find the amount of acid. And in chemistry, dimensional analysis, you would have 2 moles of acid for 1 mole of base as your dimensional analysis work. So if you plug this into your calculator, you would get 0.0162. Sorry, I'll write this above. So you would have 0.016324 moles of acid. If this much, you would have this much acid. Now you have moles, right? So now we found out that we have this many moles of acid. And we can see that we also have the volume of the acid. So we can find molarity, aka concentration. So 0.016324 moles over liters, right? So in this case, it would be 0.01002 liters of acid, and you can find the molarity. So 0.016324 divided by 0.0102, your molarity should be 1.6 molar. 1.6 molar, and then your acid, which is HCl. And we round to 2 sig digs because of this. So that's going to be our answer, right? So all we did, this might seem really complicated. All we did is, based on the information of our base, we found the moles of base. Then we used the mole ratio to find the amount of moles of acid. In this case, there's 2 times as much acid as there is base. So we just have to multiply the amount of moles of base by 2. Now we have moles of base. Now we have the liters of base. That's what we're given. So we can find the molarity of the acid. We have the liters of acid. We have moles of acid. We can find molarity of acid, because molarity is moles over liters.